Our next speaker is a research scientist who specialises in modelling and simulation of physical systems and works on a number of projects with a focus on computational geometry. In today's talk, he'll be showing us how to use Python for computational geometry. Please welcome Andrew Walker.
Better? Yeah. Good afternoon, everybody. I've been introduced, but this is my colleague, Daniel Cousins. Daniel's actually a Swinburne University industry-based learning student who's on attachment to DSTO for 12 months. DSTO is the organisation I work for. This talk itself actually came out of some of the things that happened at this year's US PyCon. I actually attended the science sprints with the IPython team and the Pandas team. And some of it came out of my frustration with the lack of availability of really good computational geometry tools in Python at the moment. So what is this computational geometry thing? So this is the Wikipedia definition. It's a branch of computer science devoted to the study of algorithms which can be stated in terms of geometry, which is kind of a bit vague, but it's things like shapes and intersections, triangulations, meshing. But what does that actually mean in practice? So there's a ton of applications for computational geometry. Tennessee came up and spoke yesterday about virtual robotic car racing. I know there's other people in the room who have a significant interest in game development, doing collision detections in games. There are other people here who are GIS people. There's already great tools for things like Shapely to do unions and intersections of geometric regions in 2D. But where it starts getting hard is when you've got the science problems, and that's what our interest really is. So when you're trying to do computer-aided design and manufacture, computational fluid dynamics, how fluid moves, and finite element analysis. Now, I'm not saying I'm an expert on any of those things, but they're an interest, and we do use some of these tools in the same way that the professionals in the industry use them. So why would you use Python? Everybody who's here knows you use Python because it's awesome. But really, it's about rapid prototyping for us. So it's how do you actually turn something around from a concept to code to a visualization to an explanation to somebody, one of your clients. For us, another big thing is that it's free. So a lot of the commercial scientific software that's out there at the moment, it's pay per seat or pay per site. And when you have to actually distribute this across clusters and large computers, it can become challenging. So additionally, you've already got really fantastic support from the scientific community working in Python. Things like NumPy and SciPy really make addressing some of these problems much easier, especially with the post-processing of results. I've got a list of some of the interactivity and visualization support packages as well. So we use IPython to actually drive a lot of our simulations and to control and manipulate them. We're using Matplotlib for 2D plotting, Nthoughts Maya VI for 3D plotting, and we're starting to look at using things like Charco for really interactive plots where you can drag sliders and actually give those things directly to your clients. So what are the challenges? Computational geometry is hard. Who's written computational geometry code, intersections or triangulations, and had them blow up because of some crazy edge case? It really is hard to write robust code. So one of the simplest examples is if you have two lines that are intersecting, you can have an obvious intersection, you may have no intersection, or you may have the horrible case where the two line segments actually overlap. So you've got to be able to detect, in particular, that third case and be able to differentiate it from the first two. And so once you've actually got the robustness side of things going, how do you actually convert that code to being robust and to being reusable? So a lot of the tools that we'll look at are C++ codes that you face a combinatorial explosion of possibilities for combining different components together. So we're not just looking at Euclidean geometries in 2 and 3 dimensions, but spherical geometries as well, where things will wrap around surfaces. It's also exceptionally hard to write algorithms that are provably correct, and that means it's hard to test. So, yep. So another issue is a lot of the resources that are available are pretty C++ centric. This is a really great book if you're getting started writing your own code. The other book is the O'Rourke book, which is starting to get a bit older, but it's still a great book if you're trying to do that. Most of the time, you aren't going to want to try and write this code yourself. You're going to want to use somebody else's. So Python is great because it's a fantastic glue language for doing these things. So we're going to talk a little bit about SciPy, Weave, and Boost Python. So, what's available at the moment on PyPy? If all you need to do is basic geometric intersection, say for some game programming stuff, you can use Euclid. If what you're really interested in is meshing and being compatible with something like Mathematica or MATLAB, you might want to try MeshPy. Now, I'm hoping that SciPy is going to end up with a geometry module. I think that would be the ideal direction for this stuff to go in. It doesn't at the moment, but it does have SciPy Spatial for the last few releases, and we'll demo that in a little while. The last link there is GTS, the GNU Triangulated Surface Library. We're gonna ignore those packages though for today, and we're gonna focus on one other library. Yep. This presentation is going to talk about the Computational Geometry and Algorithms Library, which is a research project run out of a few companies in France and some of their universities as well. And more specifically, we're going to talk about Seagull bindings, which is a Swig package that wraps those bindings up and makes them available in Java and Python at the moment, and potentially Ruby in the near future. So the rest of the talk is structured a bit differently. We're going to have a question and then some diagrams, and we're going to actually show you some of the code that you would use to actually solve some of the problems that are interesting when you get started in computational geometry. So this is the case that I was speaking about before, where you've got your line segments. So segments are actually a specialization of a line, and lines in geometry are actually infinite. So we've actually got 2 points that define a short interval on a line. We've got the intersecting case, the non-intersecting case, and the overlapping case. So if you're going to implement that with Seagull bindings, it might look something like this. We're pulling in the kernel, and we're using the points and the segment objects that come from that kernel, and then we can actually start testing intersections. And once we've got our actual intersection object, we can start to pull more and more information out of it. So the message from this is, if what you want to do is simple intersection tests, planes, spheres, triangles, triangle meshes, lines, segments, and rays, pretty much everything that you'd need to do a basic raycaster or most types of scientific simulations, that stuff is here already and it's easy to get access to. So the next thing that normally comes up is, all right, I have this problem, I have some points, or I have a polygon, except this algorithm over here only wants a set of triangles. So how do I actually convert my convex polygon back to a set of triangles? So let me show you some pictures. So there's my set of points, and what I'm really going to do is, if you can imagine, I had a nail board and I banged nails into the board for each of those points, and then I got a big elastic band and stretched it around the points. That would actually be the convex hull of those points. I can then actually start trying to link some of these points up and form all the triangles that enclose the equivalent area inside that convex hull. So moving on to the code. Yeah.
You're probably noticing that this looks pretty similar to like an ear clipping algorithm at the moment, and that's just one of the simple things that we can overcome by using a constrained denominator, which is what we're going to go into next after this one.
Okay, so here, again, we're pulling in the Seagull kernel and grabbing the triangulations package as well. We've got a little bit of NumPy glue code to actually set up our points, and then we can just insert those into the triangulation. What I'm not showing is the actual reasonably boring matplotlib code to actually generate the diagrams. But once you've got that triangulation object, you can enumerate the vertices, the edges, and the faces, and information that's associated with them. Okay, so that's good for the simplest case, right? But for the scientists out there, they look at that triangulation and go, that's not helpful. It doesn't actually solve the problems that I want to solve. I need coarse meshes in the areas that I don't care about, and I want finely resolved meshes on boundaries. So here's my geometry. I've got a spanner, say, and I actually want to solve for the stresses and strains in the head of the spanner when I'm pulling on a bolt. So what's going to happen is each of the points in the geometry are going to end up being added as points, and then we're going to actually add interconnecting segments between each of those points. So once we run a triangulation on something like that, and we're going to need to use a slightly different triangulation to make sure those edges definitely show up, so that's a constrained Delaunay triangulation, we end up with something like this. So you can still see that there's a few triangles there that we probably don't want, so we're going to have to get rid of them at some stage. But before we do that, we're going to actually jump in and we're going to refine the mesh. So here, this is something that's a bit more like what you might want to convert to, say, matrix form, so you can actually feed it to a solver. There's still a whole heap of artifacts, and in fact the artifacts have gotten a little bit worse. But we're going to add a bit more information. We're going to actually say, this is outside the polygon, and this is outside the polygon of interest as well. And so once we do that, we can actually run a test, and we can filter everything back to our actual spanner. So again, I think the big thing here is that this is not a lot of code, and that was a really complicated geometric problem to solve. There's a little bit of code to actually go through and insert each of the points and segments in that polygon as constraints, and handle the wraparound case as well. We've got just a little bit of code that's not shown to go and find the polygons from disk, which I kind of pre-calculated earlier. And then the stuff at the bottom is actually the refinement process. So again, the triangulations that you get back from this process work the same way as they did for the last step. You can still enumerate the vertices, the edges and the faces, and any information that's associated with them. Okay, so we're going to take a little bit of a detour here, and we're going to show some SciPy spatial stuff. So say I have a cloud of points, and I've got a particular query point in the center of my domain. It's not particularly visible. So what I'm actually looking for is the k closest neighbors or points to that query point, or I might want the points that are within some fixed radius of that point. So that might look something like this. So it's easy to actually write this code. It's probably a one-line list comprehension to actually do it naively. What you might want to do, though, is say, all right, that's not performant enough for what I'm trying to do. I actually want some kind of spatial partitioning routine to actually speed this query up, because I'm going to do it hundreds or thousands of times. And here you can see that we're generating some random points. We're adding them to the KD tree, which is a spatial partitioning tree, which progressively refines the environment by cutting each domain in half. We're adding our query point and then looking for the points that are within some radius of that. So this is actually a three-dimensional example, and Dan's actually going to show an example of what that might look like if you render it using Maya VI. Yep. So you can see the points moving kind of helps you see the unit box that they're distributed in, and the actual red points that are the closest neighbours to the centre of that box. I think one of the things for me about that is not a lot of code to actually have something up and visualised in 3 dimensions. Okay, so this is kind of a bit of a pet project of mine. I've been working on it for a while, but I'd like to know how to actually generate a mesh, a surface mesh of a function in 3 dimensions. So that helps you do all kinds of constructive solid geometry tricks eventually. So here's the function for a sphere, and say I take that a bit further and I've got the function for 2 spheres. You don't have to actually understand the maths for any of this, but all right. So the important thing is that you can actually understand the code. So here's the code to generate a sphere, and here's the code to generate multiple spheres. this example itself is actually using SciPy Weave. So we've hit the limits of what it's possible to do with Seagull bindings at the moment. And there's a little bit of hand waving going on. We'll show some of the extra code that's in C++ in a minute. But the SciPy Weave call, the code and the support arguments are on the next 2 slides. We're basically bundling up a whole heap of arguments to that create mesh function, and that gets passed through with the correct type annotations to the C++. We need to link in a few extra libraries. So let me give you a taste of what it would be like to do this kind of stuff in C++. So this is the support code. So up the top, there's a whole bunch of hash includes. There's a whole bunch of type defs that are all chained and interdependent, and there's a huge variety of possible combinations of those things. All right, the pi object implicit surface function in that third block there is probably where things start getting interesting. SciPy Weave actually includes wrappers that you can pass. You can pass Python objects into C++ code and interact with them. So the generic surface function at the bottom is actually unpacking C++ parameters, repacking them up into something that Python can understand, triggering that global function, and then unpacking the result and returning it. Yeah.
So you can see it's just basically in the Seagull code that we just showed here. It's calling the function sphere, and then it's basically generating all the points on that sphere through that callback.
Yep. 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 And so this is where we actually start to see the arguments that we had in the first of the 3 slides. So the surface function is our sphere function, and then the angular bound, the radius bound, and the distance bound are all the pieces of information that we had to pass in. We do our actual surface meshing, and then we can dump all of that geometry to disk. So what might that look like if you actually tried to run or visualize those results? Yep. So like you might expect, it's actually used that function to actually populate points on the boundary of the sphere, and then it's actually run the triangulation on that surface for you. All right.
Just one thing to be important to know is this is a surface mesh, not a internal. So if we just sort of go in there, I think we should be able to eventually get in next.
Yep. So that's actually inside the sphere. So I think that's going to be more important and clearer when you actually see the next example. So this is useful and very interesting if you're doing things like game programming and trying to actually generate boundary meshes. But in the sciences, it's perhaps a little less interesting. So what we're really looking for is, imagine the spanner example. Okay, it's not enough just to have a 2-dimensional mesh. You really want a 3-dimensional mesh. So if you consider what that actually means, we're looking for a tetrahedral mesh in. Yeah. We're looking for a tetrahedral mesh in 3 dimensions. So each of the you have 4 points that make up 4 different triangles for each element in the mesh. Just go back to the slides for a minute then. Yeah, that's perfect. Yep, next slide. So this is the actual problem that we're trying to solve that I was talking about. And so the code to do something like that looks like this. Okay, so again, very similar to the 2-dimensional example, except this time we have to provide a bit more information. We're really looking at how big are the facets going to be on the surface, and how big are each of the cells going to be. And then we can actually do our refinement process and dump the geometry out to disk. Yep. And so that's a quick picture of what they might look like, and I think Dan will try and, yep, there we go. So that's the actual geometry itself, but it's still, we've actually cut it in half to make visualizing the results just a little bit easier. But if you actually open the pipeline up and actually turn it into a wireframe mesh, so surface, yep, actor, yep, yep. So now you can see that there's a huge number of interconnecting edges for each of the tetrahedra inside that mesh. So we'll show you a second demo in a minute, but it's probably important just to see and get a bit of an idea about how coarse that mesh is, because the next one we show you is a bit finer, so you actually have some scope to actually change the parameters and get the mesh refined in the way that you want. Yep. So again, you can see that the triangles on each of the facets and cells are actually significantly smaller. Yep.
Could show you the inside, but it's pretty much just going to be a wireframe mess, right? So
yeah. So we've talked about an awful lot of different packages inside Seagull and inside SciPy. So I just wanted to actually present just a little bit of a summary slide just to remind people of where we've been. If you're looking for basic intersection tests, you're looking for Seagull kernel. If you're looking to do triangulations in 2 and 3 dimensions, there's triangulation packages, there's mesh refinement packages. One of the things that we didn't think we were going to have time to do, but I think we might have, is the alpha shapes examples that you can use to refine point clouds back to boundary meshes. And of course we talked about SciPy Spatial for doing the nearest neighbours problem, and SciPy Weave for doing some native code integration as well. So thank you very much for taking the time to come along and listen to us today.
Thanks, guys. If anybody's got questions? Questions? Wait, there we go.
Frank Sainsbury. You were talking about animating the changing of the positions of nodes, I thought, at one stage in your talk. Is there an example of that sort of thing?
Animating the 3D visualizations?
Or, yeah, I thought you were talking about interacting with the nodes in some way, but perhaps I missed that or misunderstood.
There are some libraries, Charco in particular, that will let you do some interaction. We're still really just starting to get started with that stuff, and you know, it's very early days. I think we'll continue to look at it though for some types of problems. Yeah.
So what sort of limits did you come up with the amount of points that you can put into your k-dimensional map?
It's n-dimensional, so I mean that's probably the first thing for the scientists in the room to know. We haven't pushed it as far as we probably need to actually give you an answer to that, but yeah, it would be an interesting thing to look at.
Yeah, g'day. The actual Seagull kernel with the intersections and things, does it handle other spatial relationships like points contained within shapes, things like that?
The triangulations definitely do. There's a point contains test, a location test, I believe it's called. For some of the others, yes, it does, but I'm not sure whether that's exposed in the Python bindings at the moment. So they've very much prioritised the things that they need to get done to address their particular research concerns. But there's a very active developer community, and I can see those things coming in the near future.
Hi. So you said you could do point cloud and turn that into a mesh.
Yeah.
Can you just elaborate on that? Does that mean you can like scan a 3D object and turn it into polygon mesh?
There is some code in Seagull for doing that. So there's some surface reconstruction code, but that is definitely not in the bindings at the moment. So if you want to get involved, you can go and have a look at the Google Code project. I mean, we're certainly not involved. We don't own the project. We're just starting to make some contributions. But yeah, they're looking for as much help as they can get.
You
you talked about writing out to disk.
Yep.
Do the libraries have their own file formats, or?
Most of the formats that they're writing to are actually standard formats. The OFF and the MEDIT. So MEDIT is actually a French geometry format for writing tetrahedral meshes, which is standard in scientific communities. The OFF format, you can actually access that from something like MeshLab and convert it to a more standard format like an OBJ, a wavefront OBJ, or a STL format if you need to.
What's that format they use for 3D printers?
STL, I believe.
Okay.
In many cases.
So you can export to that, can you?
I don't know whether you can export to it directly at the moment, but it's certainly trivial to actually use a conversion tool to get to STL.
Right, interesting.
MeshLab's probably going to be the best, like one of the easiest ones on Linux for that, just to convert it.
Anybody else? Yep.
Oh yeah, hi. So along the lines of the open STL format thing, there's a program called OpenSCAD which lets you do solid construction.
Yes.
Does that mean it's going to be possible to do that easily in Python in the future rather than...
This is actually something that I actually forgot to talk about. OpenSCAD is probably one of the most important computational geometry projects out there at the moment. If you haven't looked at it, go and have a look at it. It's a programmer's CAD package that will let you construct things and join them together, merge, and do difference operations. It's also implemented using Seagull, strangely enough. The important part of the Seagull library that's missing from the bindings at the moment, Nef polyhedra, is actually coming. There's actually been an awful lot of active chat in the discussion groups on doing exactly that. If you can't wait, there's already bindings in Python to actually grab OpenSCAD. So there's a GitHub project for that. So I can show you later if you want.
Any other questions? We've got time, so... Nope. Okay, well, thanks very much, guys. There's a mug and some coffee.
Thank you very
Enjoy.
much.
Please share with each other.